And okay, some background. What is this tutorial supposed to be about? So, well, since this assignment and the next assignment are coding assignments, I mean, and you guys have a midterm, and the midterm is not coding, I wanted to give some examples of, I guess, questions that you might see on like midterms or related things. And the way I did this is I added these exercises to the actual notes. So the notes have these exercises, and as per usual, I did it all last minute and uploaded only last night, so no one could check anything beforehand. However, it is there now, and I apologize again for that, but probably in the future tutorials is going to be a similar story. So I do what I can, but the point is there's going to be exercises in the notes before the midterm for sure, like at least a week before, like these ones and the ones I had next week, and then so on, that you can actually go over, and there's solutions as well for all these that are in the course notes as well, that you can basically work through and see what similar type of, and then, yeah, I'll just try to keep adding as many as I can as they come to mind and things like that. Okay, so that's the background of that. And then the tutorial today is just going over these questions from the course notes, which have solutions and stuff there. Okay. And there was also like, you can always ask on Piazza about certain topics that you want covered in the tutorials. And I start with first like a topic that was requested to be covered. So I just give like, I guess, a review of this mini batch gradient descent stuff and some things that maybe I didn't quite cover in class. So we start with that, and then we go over some problems. Okay. So mini batch gradient descent is just gradient descent, but now you don't have the estimate of the loss function basically for all the data, but for these mini batches. Okay. What does that look like? So that looks like you take the data set D and you break it up into mini batches. Right, so you have mini batch 1, mini batch 2, and this is the example just straight from the course notes. So I guess you can, it helps you understand the course notes too. And this is the example where if your data set was originally of size 8 and you want mini batches of size 2, you will now have M equal to 4 mini batches, right? Each one of size 2. What you're going to do with these mini batches is you're now going to have a new estimate of the loss called L hat of M, which only uses the mini batches. And so so it's a worse estimate in the sense that it uses less data, but the nice thing is that it's of a smaller size, so it takes less time to compute, and we're going to do these gradient descent steps in a second. But anyways, each one of them only uses B data points. So the corresponding data points in that batch. So that's what this thing describes. It's a sample mean estimate. That's why there's this 1 over B that uses B data points, and it's an estimate of the expected loss. Okay, so that's the main thing that's changed. And what does this change imply? What it implies is that the gradient is now with respect to this L hat of M instead of just the original L hat. Okay, but the thing looks exactly the same, like the gradient. I mean, we can write the gradient. So the gradient, if you recall, was just like 2 over B. That was kind of this first, the derivative coming from here, summed up of I equal to M minus 1. And I don't even know if I wrote this explicitly in the course notes, but it should be very easy to get straight from the original batch gradient that we had. And then it's xi transpose w minus yi. And since this thing needs to be a vector, I said that you can write in this compressed way where you have the xi vector out here. Okay, and I should use vectors everywhere that things are vectors because, yeah. So that's the gradient. For this, the only thing that's changed is now you have B here and you have a sum over B things. Okay, so you plug that into here. The thing I didn't cover in the lecture notes was these up rules. There's like these 2 things in the course notes, and I just jumped straight to the algorithm without saying these things because these are a little bit more technical, but like they're exactly what's happening in the algorithm. So I review the algorithm first, and then I come back to what happened here. And you should see why there's these 2 steps. Okay, so what's the algorithm? The algorithm is run mini batch gradient descent for capital T epochs, and then output the weight vector you get after T epochs after the last mini batch. Okay, makes sense. So like, what does the algorithm look like? It looks like this loop over the epochs, just like the original batch gradient descent. But now there's an extra loop over the number of mini batches you have. Okay, forget about this randomly shuffling thing. I'll talk about it in a quick second, but yeah. So there's this loop over the number of mini batches you have. And in each one of those, you just do the gradient descent step, except using the gradient that only uses the little b data points, the data points in your mini batch. Okay. So, but what's going, so notice how now, this is the important thing, is that we used to have capital T, number of epochs, batch gradient updates. Now we have capital T times M, because there's two loops, mini batch, I'll call these mini batch gradient updates, right? Gradient steps. So we now have these M steps. So what did our learner do? It outputted the weight you get after capital T steps and after M capital T epochs and after M mini batches. So that would be like the very final thing of this loop and the very final thing of this loop. Okay. So hopefully that algorithm makes sense. Now I give you the mathematical update rules. And the reason there's two of them is because there's two loops. Okay. So in particular, for a fixed T, right, you do updates over M from 1 to M. But then once you get to capital M, you then have to change T. So you would move to the next T. And then you would loop over this again. And so that's why there's just these two updates, which have now two indices. There's a epoch index and a mini batch index. So for the case of a single epoch T, what's going on is you have updates over mini batch indices. Okay, so for a fixed epoch, you're iterating over mini batches. So just saying that it's the weights at the previous mini batch for the same fixed epoch, right? And then you do this update, and then you update this index of the mini batch. That's the same thing as just being inside this inner loop and going to the next thing here. However, when you get to the end of the mini batch loop, which is this case here, so once you're on the final mini batch, you need to change your epoch number. So that's what's happening here. So when you're on epoch T and you're on the final mini batch, what you do is you move on to T plus 1. You move on to the next epoch, and you start again at index 1 for your mini batches. Yeah, that's all I have to say. The only thing, I think this might need to be a 0. So I'll add a correction. This might need to be, yeah, maybe 0. I had a note for that. Okay, and the reason I say it might need to be 0 is because I can't, or I guess we can kind of debug together, which is like, I can't remember what we start at for this index here, but I guess it's a matter of convention. Anyways, I don't want to take too long, but the point is you restart at the first index of the mini batch thing. Okay. Then there was a couple questions, which is like, for a given data set D, each mini batch has an L hat of M. Yes. So for a given data set, that data set has capital M of these guys. So you can think it has, but like, yes, it has capital M of these, but then, and they're calculated based on these things. But it turns out that in practice, and well, actually in theory too, it's useful to not use the same mini batches every single iteration. And so that's where the shuffling comes from. It turns out it's good to shuffle up the data and then choose the mini batches again, and so on. So you always have this L hat of M, but technically it's changing at each epoch because you're using a different kind of like different indices in your data set. And that turns out to be helpful. And it says, for non-even N over B, do we use the floor in practice? And the answer to that, so it's asking like, do we use the end, okay. So in the case where, like if N were to equal to 9, and B were to be 2, whatever, you'd have M equal to the floor, so it'd be like the floor of 9 over 2, and that equals to 2. But you would be missing, there's one more data point, which you'd be missing, which is like this guy. And so we don't include this, which is what I mentioned, but in practice you would include this. And the reason I didn't include this is because, like, for the purposes of running things, it barely makes any difference. But in terms of writing your code, it makes things a lot uglier. So like you'd have this loop, but then you'd always have an extra if condition right after this, which is checking if things were not divisible. So like if n over b is not an integer and it has like some decimal places, so you check it if its modulus is 0 or whatever, then you'd have to do this if condition, which you do an update, which doesn't go till m minus b, but it goes till n and so on. So basically it makes this really annoying like extra if condition that adds like very little extra data to this thing. But in practice, you would still do it because like it helps to use just a little bit of extra data. But for the purposes of presentation, it would be really annoying. And like then you would have a different L hat for capital M plus 1 because it would no longer be of size b, it would be of size n minus m times b, and all these like annoying cases which just I think make everything more complicated while not really adding much value in terms of understanding. Okay, so, and then maybe I just mentioned one thing which some people saw in the assignment, and I actually just posted about it a few minutes ago, so you'll see the thing. But in this random shuffling of D, the way you should do this in the assignment is that every single time you should shuffle the same data set. Okay, so you should shuffle the same D. What you should not do is you should not override D and then shuffle the D, and then override D and shuffle the D. Okay, so it should always be randomly shuffle D, not randomly shuffle the D you just got from randomly shuffling it in the last step. Okay, and I explained this a little more detail in the post in the Piazza announcement, but some people were having this problem. Okay, that's all I have to say about mini badge gradient descent. And for the rest of the stuff, I go over some exercises that I wrote up related to all, this is all chapter 6, so all optimization stuff. Next week will be all chapter 7 evaluation things, I guess. Okay, so let's go through these problems. And these are also, I guess, posted, and I'll post the solutions I write up here. Okay, so they start in order of like the chapter as well. Okay, so here's the question. You're minimizing a function g, right? It's a multi-dimensional function by using gradient descent with an initial point w naught. Okay, and some step size, this constant step size. So then you run gradient descent for like a lot of iterations, 10 to the 6th, which is like 100,000, right? Or a million. It's a million iterations. And then you get your parameter after running this gradient descent thing. The question is like, can you be certain that this thing is actually equal to w star, which is the minimizer of this function? Okay, and yeah, this is like a little, like it's not, there's not too much to the question, but the answer is like no, you can't be certain. So you can't, so the answer is no. But then I write, I guess, in blue, but g of this wt, right, will be very, very close. So like very, very close to g of w star. So it's very likely that these will be very, very close or almost identical. But like with gradient descent, the story is that like you can run this thing for any finite amount of time, and you can never be certain that you get to the actual minimum, but you're always getting closer and closer and closer and closer. Okay, and you only can be certain if you run it for infinitely long. So it's like the result says like as t goes to infinity, then you get the thing. But like at any finite time, you never quite get it. Okay, so this seems like a bit of an exaggeration, but the point of the story is that like you never really get to w star. You're always getting closer and closer, and like as you increase this, you get closer. If you choose your step size correctly and stuff, or like pick a good step size, then the rate at which you approach things will be better. And that's why you have these different step size setting techniques, but you're never quite sure. The only way you can kind of see this is if you plot, right? You can plot this function. So you might plot this thing. So this is g of w, and I guess w of t. And this is kind of how you get an idea that you've made it. So this thing is your, I guess, your capital T that you pick. And as you increase the capital T, what you're going to see is that this function is decreasing and decreasing and decreasing for your W. And you'll get something like this eventually where it's like, it's just not moving at all anymore almost. And at this point, like somewhere around here, you can be pretty sure, you know, that you've run it for long enough. Like there's barely any change, so you're pretty sure you're at like the minimum point at this point. So that's what happens. And I mean, you did this in the first assignment, you plot, this was number of epochs, right? And this is like what's done in practice, right? This G function is now your estimated loss. And in practice, you actually do this. Like you plot this thing over time. And time here, number of epochs, goes over weeks and months, right? That they're running these, like for instance, when they trained ChatGPT, they were running this for literally weeks. And they were having live plots of seeing its a, like estimate of its loss. Like literally, they have a loss function, and they plot this thing. And they look over time. And once they see that there's barely any gain, they will just, like, they're happy with stopping to run it. But you could still keep running and get a little bit of benefit. Okay? And yeah, and then the other, like, that's the story. And you can change like the step size, and there's other like strategies you can change to make this thing go down faster. So like this would be ideal if you can go faster. And maybe like there's various reasons why this thing might not actually be able to reach W star in more complicated things. And so you actually can get something that, but anyways, the story is you really do plot these kind of things over time. And it's when you see that you're barely making any more benefits, you're barely getting any benefit from this, you just stop. Okay, that's a long story to answer this short question of not knowing this. Yeah. That's right. You can never be sure, but you can probably be pretty confident if it also is not changing like at all anymore, because then your gradient is like, if your gradient gets to 0 and then it's not moving at all, then you can be pretty sure as well. Like for instance, imagine you had this like case and you started here and then you like moved here as your next point, right? This is how you can kind of, and then you moved here and then you got lucky and your next step moved exactly here. Then you would notice that the gradient here is 0 and all of your updates, your future updates at whatever t plus 1 thing, will now equal to wt, which is this point, plus eta whatever t, times 0, because the gradient is actually 0 at this point. So if you got like exactly at that, managed to hit it exactly, then you would just, then you're at W star at this point and everything's okay. But most of the time that doesn't happen, so you always have a little bit of something going on here. And then you're always moving around a little bit. Oh, and there's a minus here. And so I mentioned a little bit in the notes, but like, that's also another reason why this decaying step size is kind of important, is because like to actually get to converging to this minimum, like eventually over time, you actually also need this term to also decay to 0, because otherwise you're always going to be jumping around. Well, okay, unless you get perfectly on the spot, but there's a case where you could just constantly be oscillating between the two. So in the theory world, you actually need this thing to also decay with time. Okay. So that's the story of this, yeah. And like, if you could just solve in a closed form solution, you could do that and get this thing immediately. But usually, you just don't. There's no closed form solutions for more complicated function classes. Okay. This is a very easy one, the next one, but I guess so it says, suppose you're using the exponential decaying step size. So recall the exponential decaying step size is like eta of t guy equal to eta times the exponential of minus lambda of t, right? This thing is t. Okay. It says, suppose you're using this. Is there some way to set the parameters eta and lambda, which are these guys, so that you're using a constant step size? And the constant step size, so this is exponential decaying, and the constant step size like this. So the answer is, it turns out that if you set lambda to 0, then this thing equals minus 0 times t, which equals to just the exponential function at 0, which is 1. Okay, so the point is that this thing is strictly more general, and same with the inverse decaying one. Like, you could set the parameter lambda in such a way that you just retrieve the constant step size again. Okay, so like you don't need to really implement constant step size ever. Like if you implement one of these, you just, when you want constant step size, just set lambda to 0 and you get back the original one. And someone asked, like, is that where step sizes come in to make it faster? And I think it was related to the previous thing, which is, yes, like setting the step size is like a very, very important part as to how fast these, like how fast you end up getting to this minimum. Like you might find that you get a plot like this, which also eventually gets to this minimum point, or you might get a plot like this, and these will, assuming that all of these are going to the same minimum. Okay, maybe I make this even more dramatic. You like get something like this, and these would all be just different step sizes. These 3 lines. So you change the steps, you'll literally see 3 different plots like this. And I think in the first assignment, you see that as you change step size value, you would actually like with that slider, you see that these lines are changing. There's like a step size that really gets you to like really quickly to this, and there's step sizes that get you there, but they take really, really long. And so that's what you were plotting. Okay. Those are the 2 questions. Exercise. Yeah, there's 10 exercises that I added, and I think they get a little more challenging as we move on. So the question is like, what would the badge gradient descent update rule be if we used the loss function? Oh yeah, this is a bit of a longer story. So yeah, so we had badge gradient descent update rule, if you remember. And now we're going to use a different loss function, L, which is this like to the power of 4 instead of the squared one. Okay, so in a sense, if you're farther away from y, like before, imagine you were like, your estimate was 2 away, you would have had 2 squared as your loss, so you would have 4 as your loss. Now you have 4 squared, so you really penalize estimates that are farther away from correct. So like you really don't want to be far away from this. Okay, so it just weighs things differently. And similarly, if you have a point really, really close, like 0.2, let's say your loss was 0.2, now 0.2 to the power of 4 is a much smaller number than it used to be. So there's this difference in scaling. No one really uses this in practice, but like this is a good exercise to test like that you don't have to be limited to just one of these loss functions. And I mentioned one thing kind of in passing is like, you may have noticed I've been constantly avoiding this absolute loss. And the reason is because it technically doesn't have a derivative, or it doesn't have a gradient. Right, at the 0 point, it has this like discontinuity, and what you have to take is this thing called a subgradient. And I didn't want to deal with these technicalities, but the story is it's almost the same thing. And yeah, like you can, yeah. So, but I don't want to ask you these things because I don't want to go into more optimization theory and stuff. But like the ideas are all the same. You really want the gradient. It turns out you have to work with the subgradient thing, but then the update rule is exactly the same. You just replace gradient with subgradient. Okay. So let's start the first part of the question, and then the second part is asking like, what is the one-dimensional case? Is this thing convex? And we'll talk about that in a second too. Okay, so what's the badge gradient descent update rule? So remember what that is. It's this guy. It's W of t plus 1 equals to W of t plus, why do I keep writing plus? Minus the step size at time step t, right? Multiplied by the gradient, and this is where the gradient part comes in, of the estimated loss of W. Okay, I guess I write vectors everywhere. Okay, and the important thing to point out is this thing is based on L, the loss function, right? So that's what we're changing. We're changing the loss function. So this gradient is going to change. So in order to see how that's going to change, let's write what L hat becomes. So our L hat, and I'm going to write it just for an arbitrary W, so I don't have to keep carrying this T, is 1 over n, sum I equal 1 to n of, I write it the loss function of X transpose W minus, comma. Okay. This is what the estimated loss is. And now we plug in our loss function that we were given. And I can almost assure you that there's going to be things related to this, definitely on the terms like changing loss functions, then how do gradients change, like what's the new update rules and things like this. Like we're using the most common one kind of in the stuff, but then like you should understand like you can change this however way you want. Like I could have added a multiple of like 2 here to make things just twice as large, or I could have scaled it by less, or I don't know. And we'll see another like an actual loss function that we use quite soon when we get to classification, and that one's much more complicated to take derivatives of and stuff as well. Okay, so let's get back to business. I plug in the actual loss now, and that is this xi transpose w vector minus yi to the power of 4. Okay, and all that's left now is for me to take its gradient. And for the sake of time and I guess space and everything, and like just to show you how this can be done maybe a lot quicker than what we did in class through all this chain rule and everything, I do like kind of a shorter version that after doing this a couple times, you'll see that it really does work, which is like, let's take this gradient, okay? So what is the gradient? Well, now like, okay, it's going to be this giant vector things of L hat with respect to dw0 all the way up to, the reason I write this is because you notice that the only thing that changes is the derivative with respect to which w you're taking the partial derivative of here. Okay. And this thing is a vector, of course, and d plus 1. So all I really need to do is just compute any one of these. They turn out to all be some like the exact same thing. So I just need to compute this for a single like W1, W2, whatever I call Wj. So to compute that, I do this in a very quick way. So I look at this thing, okay, and I need to compute this derivative, and we went through all these steps before and stuff, and maybe you remember the derivative, maybe not, but you can do this derivative in this way. So you can, first of all, the first thing you should note is that the derivative of a sum of things is the same thing as the sum of the derivative of each one of those things. So this is the same. Oh, not L hat. The derivative with respect to Wj of what? Well, okay, I make some room. So what is the function at the top we're taking the derivative with respect to? Now it's this xi transpose w. Right, this is the function we're taking the derivative with respect to. And maybe I write even bigger brackets to say this is the function. Derivative with respect to that. This thing is a partial derivative symbol. And this thing is the partial derivative, and then it's the partial derivative with respect to Wj. Okay? And this thing will be a function of W. So you write this, and then all that's left is to take this derivative with respect to Wj. And if you write this thing out like as a sum or explicitly expand it and stuff, and I leave that as I guess an exercise for you to just explicitly write it out, but what you will find is that the derivative of this can be taken in 2 parts. First, you take the derivative of the outer function, which is the power of 4 function, right? It's this thing raised to the power of 4. So the 4 factors out, and you get the number 4 here. And then you take the derivative of the inside thing, and we've already done that. When you expand this thing inside, you'll find that it's like xi0 times w0, xi1 times w1, and so on. And if you just go back to the batch gradient thing, you see all these steps. And what you'll find is that the derivative of the inside, which we have already, okay. So first of all, we took the derivative of the outside thing, so I keep that term. And you change the power from 4 to 3. And then the derivative of the inside just ends up being xi, and for the corresponding index j. Okay. So that's the whole derivative. The only thing that's really changed from before is this is a power of 3. It used to be a power of 1. And this is a number 4 instead of a number 2. Okay. So yeah, then you plug that in to here, and you would get back the corresponding gradient. That's the story. So that solves the first part, really. The steps are very, very similar. But you should be comfortable with like this idea of you can take this derivative, like working with sums is you can move the derivative inside. Because the derivative has this property, and I mean, you can prove it and work it out, but it has this property where the derivative of a sum of things is really the sum of the derivatives. Very important. And then you apply the chain rule here, which I just did quite quickly. Okay. Next question is asking, in the one-dimensional case, and with no bias term, so you just have W as an element of R, okay? Is this thing convex? And remember the convexity, like how did we check if something was convex? We took its second derivative and checked if it was always non-negative. So we just need to take the second derivative of this thing and check if it's non-negative. So in the case where you just have W as not a vector, this derivative is just the derivative, just the regular derivative with respect to W. So let's write that. So you would write D. Okay, so this is like 1D case. Okay. So then it becomes just the first derivative of L hat with respect to just W, because there's only one parameter, function of W. Well, that's equal to 4 over n. Exactly what we had, except now I don't have to write all these vectors. And that's why I did it, because then the second derivative gets more annoying with vector stuff. Okay, and then you just have x I W minus yi cubed xi. Beautiful. Okay, and now all I need to do is take the second derivative of this thing. And that turns out to be also pretty straightforward. So it's written as like D2 usually in this version of notation. dW2 yes, of L hat. Is it like this? Maybe it's like, I think it's like this. Whatever. I think it's like this. It's just notation. It's a second derivative. You could have just wrote L double prime as well. Same story. And so this thing turns out to just be, we can use the same business as before, which is we take the derivative, like we're taking the derivative of the previous derivative, and we can move the derivative inside the sum. So we would get that this is the first derivative, right? So the second derivative is the first derivative of, is the derivative of the first derivative, right? So I can just work with that derivative. And that's what I'm doing here. And now I'm going to take the derivative with respect to this giant thing here. And that's a function of W. So I just need to compute that derivative. And that turns out to be quite easy again, because this is just a constant, right? It's just a number. So then I just take the chain rule. So that the 3 comes outside. This becomes a 2 now. And then I take the derivative of the inside again. Okay. And all that gives me that this is 4 times 3, because the 3 came out, so it's 12 over n, times the sum of I equal 1 to n of, and right then, so this xi was just a, okay, we need more room. Here's what needs, let's make some more room. So 4, I write this explicitly, I guess. It's 4 times 3 over n, right? The 3 came out. I equal 1 to n. And then the derivative would have been, you had this xi w minus y to the 2 now, yi. You have this xi was the constant. And then you have the derivative of this inside, which is just the same thing as before. It just becomes xi. So you get xi again. Okay. That's it. So compressed version. Okay, now the question was, is this thing convex? Which means, is the second derivative always non-negative? And the answer to this is yes, because you look at this guy, it's a square term, always greater than 0. You can't have something squared be less than 0. You look at this guy, also always greater than 0. And this thing, of course, is also greater than 0. Just a number. Like n can't be negative. Sorry. Okay, so at this point, you find that the whole thing is greater than or equal to 0, so L hat is convex. That was the whole point of the story. So similar to the squared loss, this, maybe you can call it a quartic loss, is also convex, right? When we use this version of L hat where we have these like linear functions in here as well. Notice it had this, the important thing was also that we had linear functions here. If we made these things something different, which is our function class wasn't these linear functions, then you'd also have a problem. Okay, so this is the case. That was a bit of a longer one, but I can assure you that this will be asked again at some point somewhere. Okay, so question was, why do we need this bias term at all? I think it's for the feature vector, but I'm not sure what its purpose is. Yeah, and so the bias thing, I can just, the thing is that, like, the way to think about it is always for drawing, like, the visually. It's just like if I wanted to plot a line, so I want to write a function, f of x. And if I write that function in one dimension, I write it in the classic form, which is like this mx plus b form, right? This thing is called the bias in this mx plus b form. And this thing would be like w1 that we use. So similarly, this is like bias or w0 that we use. Okay. Imagine we didn't have the bias term. Well, then what happens is we're really restricted to lines that can only go through the origin. Why? Because when x equals 0, this thing's always 0. So that's the problem. So this is like no bias. And then this is the version with bias. So this is with bias. And in particular, the bias here would be like b, which is the same thing as w naught. And so this is the bias. So when you set x equal to 0 here, let me show you. In this case, f of 0 equals to b, which equals to w naught, whatever, in our case. So at 0, you get this point here. Okay. So that's why you need the bias. And I mentioned one. So we keep seeing this in the 1D case, but what happens in the 2D case? Well, in the 2D case, these linear functions are planes, and the bias allows you to shift the plane up and down. And I can't really draw a plane, so I'm not even going to try. But you can, without the bias, you'd have a plane that always goes through the origin. But now you can have a plane that goes up and down. And then in 3 dimensions, you now have like 3-dimensional things called hyperplanes, but they can always be shifted. And that becomes a useful thing to have. Like, it would be really unfortunate if, like, I don't know, for a house with age 0, like a brand new house, you had to predict 0 price for it. That would be really unfortunate. Like, you really want to predict the true starting price, and then after that have a decay, like a line. You probably want something like this for maybe not a house, but a car. Maybe a car, the car prices should really go down like this. And this would be like the starting price of the car when you first buy it, and then it goes down. So you want that bias. You want to have that power to do that. Do you still have the question? So it's it doesn't say how the update rule would be used. It's asking what would the update rule be if we use this loss function. So it'd just be like, so in the, I'm sure on the midterm stuff I will, well, I'm not sure, but I hope I will make things even more explicit, which would be like, if this is the update rule for batch gradient descent, and this thing is defined as follows, and I change L, or I set L to be this is the definition of it, what is the corresponding update rule? What does this look like? Okay, I guess I didn't really fill in all the details, but the update rule, you know, just like whatever we calculate for the gradient, plug it in, you know, plug it in there. And in particular, there's maybe like, yeah, that's it. That's right. Yes, everything stays the same. And that's what we see with, so this was our general gradient descent update rule. And by general, I mean like, it was general when this guy was G of W of T. This is like the general case. And now all we've done is we said G is L hat here. like with the squared loss, that's what we said in class. Here, G is now L hat with this thing, and like, you know, like it's not clear from here that what loss you're using. So that's why I make it like I say based on this L and stuff. Like otherwise, it would be annoying having to like explicitly have some other index to describe it and stuff like that. So I just tell you in words usually. But yeah, so like the thing that changes in every, like for gradient descent is just what function you're optimizing over. Mini batch gradient descent, this L hat changed as well. It now was no longer summing from 1 to n, it was summing over batches. So notice how like the things that are changing in all these cases for gradient descent is always the function that we're taking gradients with respect to. And yeah, there's, yeah, the choice of function. Oh, I guess I should finish the question maybe. Let me, yeah, like maybe I'll do the version that I would actually like, that like possible correct answers that you should be selecting from. And like, this is not really the end of the story. There's like this extra step where you got to this guy, then you have to plug it into here. And it turns out you can do some like simplification that makes it look even nicer. So let's do it. So you had this guy, let's plug it in, and let me show you the whole thing. So once I get the simplified version, I will then just plug it back in to this equation here. But first I want the simplified version of the gradient. In terms of vector form, it would be quite nice. Okay, so what is this thing? Well, this thing, so notice how there's this 1 over n, this j does not, so this 1 over n doesn't depend on j, the 4 doesn't depend on j. So I'm going to just take these all out. It's going to be 4 over n. And now it's multiplied by like this, okay. Should I do, yeah, let's do, so notice this thing also doesn't depend on j, right? The only thing that depends on j was this, like this xij here. So I actually take everything out because I can, yeah, hopefully this makes sense. If now we can add the extra steps as needed. So hopefully you agree that all of the gradients have this thing in common, and then they are all multiplied by xi0 up to xid. That's the j's. The j's are from 0 to d. Transpose. But what is this thing? This thing is just xi vector. And so, oh, I missed the 3. That's all that. 3. And so you get that this gradient is simply 4 over n, which is the actual one we got to as well in the batch gradient descent version. The only difference is now there's a cubed here. There's a 4 at the start, but now you have this xi vector. Okay, so this is the thing that you should really do in the update rule. So in particular, what then would be a correct answer would be to take this guy and say that the batch gradient descent update rule looks like this, but not with like this, but like with the actual proper equation plugged in here. So this is the final solution. Only difference from the squared loss was you have a 4 here and a cubed here. So this is now this makes sense. This thing's a vector. This thing is also a vector. So, okay, let's look at how it's a vector. This is a number. This thing is also a number, right? It's just a dot product. This thing is a number. Cubing the difference of 2 numbers is still a number. So this whole thing, like this is a number, this is a number. All that's left is this guy, which is a vector. Okay, and then you can, yeah, so you basically have this vector, okay, it's summed up n times, but you just sum up the vectors element-wise, if you remember how summing up vectors works. And so what you end up with is that this whole thing, this is like a dimension check to make sure you like are actually working with things correctly, which is that this whole thing is an element of R of d plus 1. So it makes sense that you're also subtracting from something that's also an element of R of d plus 1. And what do you get back? You get back a vector that's in R of d plus 1. So I guess all sorts of important little details here. Okay, does that answer that for the most part? Yeah. What happened here? Okay. Let's move on to the next one. So we have, yeah, this one's, this is kind of what you're implementing in some sense in the course notes and whatever. But yeah, so remember we covered batch gradient descent with constant step size. What does it look like with exponential decaying step size? Well, what it looks like is just you need to actually update your step size at each epoch. So here's the extra line. So this is the new stuff. And it's exactly the update rule you've seen. Like this, what I mean is, this is the exponential decaying step size update. Or the value, sorry, not update. This is the exponential decaying update equation. So there it is. I've written this with like eta naught to represent eta, and then eta here because I don't write this superscript t, because you don't want to set a new variable every time step. So I reserve eta for that, and then eta naught is like your starting thing. In code, I actually, like in the assignment, yeah, I guess I mentioned all sorts of little nuances. In the assignment, we do actually pass in eta here, but then we would, in the assignment, you end up calling this thing like something like this. Okay. So then there's like these variable names and stuff, but all the same. So this is really all that's changed. And what's like, the thing is that this thing depends on t. So for every epoch, you get a new step size. Before, you just didn't have this line at all, and it was always the same value eta, which was used to be passed in here. That's all. So like similar questions would be like, of course, yeah, like, I don't know, like what is like, yeah, it does, I don't know. You can see some pseudocode of different versions of, for instance, these algorithms, and then you would have to know whether you actually implemented this step size correctly or something. So you can imagine I changed this to not the exponential decaying, but like the inverse decaying one. And this would be the inverse thing. Or if I had the like normalized gradient thing, then this should be the normalized gradient thing. Maybe it'll take a couple more steps and stuff like this. But you should understand where it goes. Like, for instance, if I did this, and imagine I put this step like, I don't know, outside of the loop for some reason, and used capital T here, then that wouldn't work. And similarly, if, I don't know, maybe if I like moved it to some, oh, I noticed one, actually, there's an important nuance here that actually would mess things up. And okay, I mentioned this about the assignment and I screwed it up here, which is this t. Okay, here it makes it look like you start at t equals 1. And this is not technically correct. So like, there's two ways to fix it. Either you set this to be t minus 1, right? Saying that like at the first epoch, you want to use this step at 0, right? You don't want, you always want to start at t equals 0 here. You want to use the 0th thing, like in the update rule, if you remember. The first update. I just show you the update rule from above. In the first update, you have like this thing, and so this should be 0 and this should be 0, right? You start with updating from W0 to W1. And this kind of notation can be misleading with the t's and stuff. So I think what's going to, yeah, for the assignment, I pointed this out with an announcement and on Piazza and stuff, but I think it might be more like, so to make this thing right here, let me make this right, is I would change this thing as follows. This is probably the easiest solution. Okay, so you start from 0 and you go to t minus 1. And I still haven't resolved how I'm going to actually, I'm going to update the notes to use this thing and mention that or whatnot. But the important thing, you really want the step size thing to start at 0. Because when you start at 0, you just start at eta naught, and then after that, you start decaying. You don't want the decay of like e to the minus lambda right away. It's similar with the inverse decaying thing. So this is important. And yeah, That's all I have to say about that. So maybe I change it to this, and this makes it more clear. And it also aligns with the indexing that you have in Python and everything like that. That's probably what I'll do, but I haven't decided yet. But anyways, quite important there. Okay, let's spend another like 10, 15 minutes going through. Maybe I go through a little quicker on some of the easier ones. So yeah, so it just says like, the next one is, suppose that we did not discard the last n minus mb data points. And maybe this was already kind of mentioned at the very beginning when we talked about mini batch gradient descent. So in practice, you wouldn't discard these data points. And instead, we use them in the last mini batch. So now we would have m+1 mini batches in the case that things are like n over b doesn't divide and it's not an integer. What would the sample mean estimate be? And this kind of points out like the annoyance of now you have these different cases. So like I can just take what it was above here. I don't know if this is going to work. I have a strong feeling it's not. But we'll see if this works. This is the original one. Oh, excellent. And this works if m is an element of 1 up to m. Okay. But we need to change it. So we need something if m equals to m+1 and n over b not an int. So this is the like extra case. And that, so I didn't want to have these two cases in the notes because it would have been quite annoying. You would have L hat of m+1 of w. And now this thing would look very similar to before, but now it wouldn't be 1 over b. You don't have b in this batch. You have 1 over n minus m times b. So that's the size of your last batch. And now the sum is not, okay, well, this I is correct. This I will now be from I equal to capital, okay, we do it very, m+1 minus 1, b plus 1. But this is, of course, just m times b. Makes sense, right? This is like you covered all your mini batches. There's m of them. And now you start at the next index. This is like the, because this doesn't divide evenly, you have a plus, like this actually a +1th index. And now you can't just go up to m times b, or like you can't do this. Because if you could, then this would be, then n would be divisible by b. And so you have to go up to n. And so that's where this difference comes from as well. And then, yeah, then everything's the same. So this, and you can imagine that in like, if I had to like go like I think it takes away from like the intuition of the story if I had to like have these two cases in the notes, and then the gradients have two different cases because now you're taking the gradient, and now in the code, you'd have an if condition handling this case. And like, at the end of the day, you just get one little extra mini batch. In practice, it's useful for like, I think for understanding, it's not that important to communicate. But that's where the exercises are for. You get to think what would happen otherwise. Someone asks, here t goes from 1 to t. And I guess this is exactly what I was just, yeah, this exact thing. So yeah, in your code, it should look like this. Or you could do t minus 1 in here. Yeah, OK. Oh boy. Okay, this question could be at different levels of length, depending on how detailed I go into this. But I give you the high level story maybe of the next exercises to make it a little quicker. So you have some function in F3. Can we be certain that F3 is inside the polynomials of degree 2? Or that F3 is an element of this? And the answer is, okay, no, we can't be certain. Okay, maybe this is actually not that long of a one. I thought maybe the next one is a bit more for details if needed. And yes, we can be certain. Yeah, I don't know why I'm writing all this out when I can just like point to it about, but here it is. Why? Well, like we talked about, this thing contains all the functions in F3 and more. So maybe, but I don't. So like, yeah, I'm just going to say that in words. in the actual solutions, I give a lot more details. I like the way you would do this, so you would actually say, and you are probably not going to need to know these details of like every F3 in here has a certain type of form, and you write it out in that form. And then you notice that you can always write that as a function that has the same form as something in here, and so it must belong in here. In contrast, you can see the contrast here, which is like, to show this one's quite easy. So suppose F3 of x was equal to x cubed, right? Then clearly x cubed is not an element of F2. It doesn't have that feature. Like that thing applies phi2. Phi2 never gives you, okay, technically this thing you should think about as x3 times the weights, which are 1. Okay? Because that's how you're actually going to see it in the thing. Okay, so that's important. And why do I emphasize this? Is because like this really builds on this understanding that the function classes get larger. Like what does larger mean? It means includes everything from the previous function class and more. And in this case, F2 is smaller than this F3, in the sense that there is an F3. I just gave you an F3. That is not, oh, what am I doing? It's not an element of F2. Important, yeah. That's what I just gave you. So yeah, this is what it means for function classes to be larger than others. Okay. Yeah, this one's just like doing the calculation for P bar and this feature map. I give you the calculation for P bar, and the feature map I don't write too much details of. So like you might remember that P bar equals to, and this is just an equation, I guess you'll be told. I think it's this, or is it? Well, let's see. If it's P, yeah, it's definitely P, because you can only pick two things here. Okay, and I thought maybe I have time to go over the details of why this is the equation, but maybe not today. And so to calculate this, it would be D plus P. Okay, so I plug them in. So this is 5, choose 2, which ends up being just 5 times 4 over 2. And yeah, that's the equation for it. You can work that out. And then you can write out the feature map. Okay, and maybe we quickly write it out. So like x vector equals to x0, x1, x2, x3. And the way you can think about creating then phi2, is you write every single combination of two things. Okay. So you have, okay, and x0 is 1. So you start with the case of 1 and 1. Right, that's like this guy and this guy. Then you do 1 in this guy, 1 in this, 1 in this. Then you do this guy and itself, and then this guy and that, and this guy and that. Then you do this guy and itself, and then this guy and that, and then just that. Okay, so all that being said is you start with the first one, then you do 1 in x1, that's just 1 times x1, that's just x1. Then you do 1 times x2, 1 times x3. Then you move on to x1. So now we go, that's the two loops that you saw in the implementation. Then you fix x1 and you multiply it by everything else. So you start with x1 times x1. That's x1 squared. x1 times x2. x1 times x3. Then you go on to x2. So then you do x2 times x2. x2 times x3. And then finally you move on to x3 times x3. And so you get all the terms this way. And yeah, that's the way you do it. It turns out you don't double count or anything. And you can kind of convince yourself why that's the procedure that works and stuff like that. Okay. This is a bit of a long one, and maybe I won't cover this one. But I give you a new function class called f bar, which is not linear functions, but it's linear functions applied with an exponential applied on it. And now I ask questions such as, like, is this function class a subset of this? Like, is f1 bar a subset 2? Is f1 is just the regular polynomials you've seen a subset of this one with the thing? How about the other way? Is this minimum true? Yeah, this is all worked out as well in the solutions. I think this one's a pretty important one to understand as well, because like, yeah, sometimes function classes are like, okay, what you'll find is the following. I give you the answers, but you'll find that, okay, this one is yes. And it's simply because f1 and f2, the only thing that changes is the phi here. And then since the phi is bigger from 1 to 2, then this thing just includes everything from before, just like in the polynomials. Then for this one, you'll find that this is a no. And the reason why is just by counterexamples. So, and I can do this, I guess, which is like, for instance, you'll have like x, I guess, in F1. That's an element of it. So yeah, that's an element of that guy. But it won't be, okay. It's an element of F1, but x will not be an element of bar F1. Because it always, the exponential is taken of it. Why do I keep forgetting the not element of symbol? Okay. And then similarly from here, you'd have like the exponential functions, which look like e to the x. That's an element of F1 bar, but e to the x is not an element of F1. Yeah, so you do these by counterexamples. Oh, then you get, yeah, so that was this direction. Actually, this one technically, ooh, this one was supposed to be over here. And that's a no for this reason. And then finally, is the following true? And I guess I can also answer this. So I'm saying that this loss is smaller than this loss when this min is over F1 bar, but this min is over F2 bar. This can't be the case because so what does this min mean? This min means you're searching for the smallest f in F1 bar, and here you're searching for the smallest f in F2 bar. But F2 bar is bigger than F1. So whatever the min of this is, it can only be larger than the min of this. Like this min. Okay, so in particular, if f star 2, which is equal to argmin of this guy, right? If this guy is not an element of, right, is not an element of F1 bar, right? So like, once again, these are all, this thing is the same as this thing. It's just the f in here that makes this the smallest. If that one is actually something that's not in here, so it's some exponential function that really needed features that use like the x squared term, right? Oh, this is, keep forgetting the not element of it. So it's possible that I could have something, this guy is not an element of this, okay? And then if that's the case, okay, since this set already like contained everything in F1, then this, what you will find is that, okay, what you will find is that L hat of F star F2, same thing, right, as min. And this is, I guess, a nice exercise of getting used to all these things of when one class is bigger than the other and so on, must be less than L, the min F element of F1. So the inequality actually goes the other way. So because this considers a bigger class of functions, it makes sense that it can find a minimum value that's potentially smaller. This is what we have in the course, right? Like, you're constantly increasing the degree of polynomial, so your mins are getting smaller. They're not getting bigger. Right here, this is saying that the min got bigger by considering more functions. That makes no sense. Right? Like, intuitively, this should make a lot of sense, like what happened here. So if you're considering more functions, you should be able to find a better minimum, not a worse minimum. Okay. Maybe I answer a question. So would we need two conditions to check if b divides n completely? Otherwise, n minus b would be equal to 0, and we would accidentally divide by 0. This is regarding this guy all the way back here. And I wouldn't be surprised if I messed up. Where is it? This guy. So if this guy's not an int, then this will not be 0. So I think it's okay. Right? So, oh, yeah, I think it's okay. So like in the case, yeah, in this case, this is, I think it's okay. This like, if this is not an int, then you do know that this really is great, at least 1. And I don't think we divide by 0. And this sum also makes sense because there's at least like this n is at least this large. So you'll at least have one element. Okay. And there's two more questions. Wow, this is a long story. Okay, I give you the short summary, which is all that it's saying is it's addressing this gradient descent story, which is like you run gradient descent on two different like cases. One that uses these polynomials of degree 1, and another case where you have polynomials of degree 2. So that means like you're optimizing this L hat 1 and L hat 2 thing. Okay, you run them both for like a long time, let's say, long enough to say that they're both like probably going to get to near their minimum. And then you ask the question is like, can you be certain that the first degree polynomial thing, like this loss, is greater than the second one? And the answer is no, you can't be certain about this, but it's very likely that this is the case, okay? So it's very likely that if you run gradient descent for first order polynomials and then you run gradient descent with second order polynomials, the estimated loss of the second order polynomials will be much smaller, especially if you even run it like that, if you run the second order one even longer. That's what this 1000 just says you ran it for 1000 gradient descent steps. However, you can never be certain. It might be the case that you run it and this thing is actually the other way around, that it's actually larger. But the way you do that is you plot these things. But this is the, and so, okay, like, yeah, there's like, for the purpose of this course, you can't be certain, but there is some, technically in theory world, there's like under various conditions, you can actually be certain that after a certain amount of iterations, it's smaller than at least some amount for sure. But we're not going to get into all these details. Like the point that this is really emphasizing is that like after some finite amount of time, you really don't know where, like you think you're going to get close to the minimum, but you don't know for certain until you like just check what it is. So there's no like 100% guarantees. Okay, and then the last question was this, like, write the pseudocode for the degree 3 polynomial business. So you saw the degree 2 one in the course notes, and you had to implement it. The degree 3 one, the only thing that changed was there's a third loop. So this is the new part. And now remember, before we did like you fix one and then you loop over all the other things. Now you fix one and then fix another and then you loop over all these. And now you get terms. So you get an extra term. So this is your extra term as well. This is also new. That's it. So now you get all things that multiply, all three multiples, like triples instead of pairs of things. And it goes on. And the story is that like this is, you can always implement this. Like you'd have for degree 4, you'd have 4 loops. For degree 5, you'd have 5 loops. And you can always implement it this way, but it turns out there's a slightly more efficient way to like do this, but we don't go over it if you needed to. But yeah, this gives the main idea across. Oh, and I guess this is also technically new because now this is bigger. It has this and 6 and so on. Okay, and I end with answering this last question, which is like, the reason why you can't be certain is because the random W vector that the gradient descent starts from is random, right? If they started at the exact same starting vector for batch gradient descent with the second degree regression, can we be certain? And the answer is also, you still can't be certain for that, even if they start at the same. Okay, first of all, they can't even start from the same starting vector, because you might remember that the vectors, okay, so I just write this really quickly. So there's this guy, and there's this guy. And they have certain forms. In particular, this guy looks like the one is for the phi, right? Okay, and I maybe right here to indicate this is W1. This is not its index. This is like for the, yeah, actually, yeah, I write the W1. And F2 is for phi 2. There's a difference between phi 1 and phi 2. This thing is the same as X transpose W1, and this implies, okay, this implies that W1 is an element of RD plus 1. However, this guy is like more complicated And in particular, phi is of a higher dimension. And so this W vector 2, and here 2 and 1 don't indicate indices, okay? These are like just different vectors that I'm using this to indicate. This thing is an element of R of P bar, where remember here this P bar in this case is going to be D, which we don't know what that is, choose plus 2, choose 2, okay? So they're not even of the same dimension. So they're actually like starting from totally different weights, and then they decay. And like here, you have to update more parameters because it's a lot like it has more parameters and stuff. So you really don't know. And it turns out that usually you need more iterations as phi gets bigger because like there's more parameters to update and it takes longer to converge to the minimum. So yeah, that's the story. So you can't really be. There's not much you can do to be certain. The things you can't, like, yeah, you really can't do much, especially when you randomly initialize the weight vector. Like, the best thing you can do in the theory world is you can guarantee that, like, on average, after some amount of iterations, you'll be this close to the minimum or something like this. But like, you can't even ensure it for every case because you might have like a bad initializations or something like this. Okay, I will end it there. Hopefully these were some helpful questions and examples.